All right, so only updates here. Final project and report and presentation. I got to copy this twice here, but it's due Wednesday. So this upcoming Wednesday, a week from yesterday. So that gives me time to do the assignments for peer reviews, which will then be due the Saturday that follows that. So that's just, mentioned here, but here and here. Muddy's Point this week, the concept check and mini project for basically Unit 7. And if you need an extra one, sort of this bonus Unit 8, which we'll talk about a little bit on Tuesday, but then that's due the not this Sunday, but the upcoming Sunday after that. The final exam is going to be all week, available all week for finals week. It's 110 minutes. Whenever you start it, the clock starts. Open book, open notes, intended to be an individual exam. So it's a little bit of an honor code there, not proctored. But, so as it says in the instructions for the exam, not something I want you to be collaborating on over Discord or Slack or anything like that. Just meant to be you and Canvas and your notes and 110 minutes. And so that's kind of the idea there. It's basically a sampling of topics from the units, kind of very similar to the concept checks. I've put two practice assignments on to give you an idea from that. One that actually does just sample from the concept checks, and one which is essentially the final exam from, I think, 2022. So that will give you an idea of the types of questions, the format, the length. It is auto-graded, so all the questions come from an auto-graded format. Whenever multiple choice is possible, it is turned on. I'm sorry, not multiple choice. Partial credit is possible, it's turned on. So if there are things where you have to match a couple of items and you get, 4 out of 5 right, you'll get the appropriate scaling on credit. And that's it. Now, so the other thing is that Thursday of next week, a week from today, then in part, I don't have a lot of new material that it would make sense to sort of shove in. And I also have to give a briefing at West Point that due to travel arrangements, it just was impossible to make Thursday work. And so so canceling lecture on Thursday. So the last kind of content for this class will be Tuesday's content. I think that's, course evaluations are open. I think they close Thursday. I don't know why they don't close Friday, but they close Thursday night. I think that's it. So any questions? Okay. So we are closing out Unit 7, kind of ending where we started. So coming kind of back to it, back to the neuron, back to the biological neuron with today's topic on spiking neural networks and neuromorphic engineering. So to begin with that, let's go back to the neuron. And this is basically the picture I drew in the first unit or the first lecture of this unit. Just your standard, you've got a couple of neurons here. So here's a neuron, upstream neuron, a downstream neuron. Neurons connect to multiple neurons, so that's where you get the so-called neural network. Your basic idea here, you got a bunch of dendrites that receive input. They generate output on an axon, and that's how they all talk to each other. That output is in the form of a so-called action potential, which we can also just call a spike. Call it a spike because these action potentials are very sparse in time. And so when you record from neurons, then they look like little spikes. So you can basically, from a ground potential, you can establish in an animal, you can then record from a neuron and watch these spikes being generated. And when this neuron gets very excited, whereas the neural networks you're familiar with, if a pathway is excited by an input so that the output is stimulated, then you might expect that output to have some high continuous value. Like it usually would sit at 0 when you're looking at a dog. When you look at a cat, it sits at 0.98 or something like that. And it sits there while the whole cat is being viewed by the convolutional neural network. And then once you show it a dog again, it goes back down to 0. In this case, the action potentials always go to the same height, so they always look about the same, but the spacing between them changes. And that's what we're going to show in a little more detail here in just a second. But so we go from spatial coding to temporal coding. And that's the whole point. That's the reason we call them spikes, is that the spikes are all the same height, but the distance between the spikes, if there's a lot of distance, then it is not very stimulated. If they're packed together into this a giant chattering mess, then that's a lot of activity. That's a high value. So high values are dense, low values are sparse. So in general, this types of communication is very sparse. There's very little activity that goes on. Most of the time, these neurons sit and quiesce. So it's this asynchronous architecture where they just sit there until they finally accumulated enough stimulus, and then they fire for just an instant, and then they sit and rest for a while after that. And as we'll get into it, your brain, that's the part, I mean, you always hear what your brain uses up almost like a huge amount of energy relative to the rest of your body. And that's true relative to the rest of your body. But your actual brain is something like 20 watts of power, so 20 joules per second, which is, it's basically a LED light bulb. It's not even incandescent light bulb, and is what's driving your brain. And it's not like if you think harder, you use more energy or anything like that. That's just it's sort of constant. It kind of doesn't matter what you're thinking of or what you're doing. That's just sort of your brain's natural activity. There might be some slight modulation with that and what you're doing, but it's not like you can lose weight by doing math or something like that, sadly enough. But it's still this doesn't it's despite using a lot of power relative to what you do, relative to the rest of your body does, it being a huge part of your energy budget. The huge reason why you have to eat is the energy needed to power your brain. Despite all of that, relative to the technology in this room that we've designed ourselves, it uses a very little amount of power. And we think part of the reason of it is the sparsity of these action potentials. The fact that so much of your brain can sit at rest, and only when it needs to signal, it does signal. And that's going to be a major motivation behind the technologies we talk about today. Okay, so just as a reminder, this gap between the axon and the dendrite is a synapse. So gap between terminals, axon terminals, and dendrites. The synapse is our location for plasticity. So it is the interface between neurons that has the ability to change its characteristics. That's where learning happens. So that's what implements learning. When after this axon potential reaches the end of this axon terminal, at that point, it releases neurotransmitters that get thrown across this gap. And so those have little transporters which bind to them, which allow them to navigate this physical distance, and then they hit receptors. So these, the number of transmitters, the availability of transporters, and the number of receptors, as well as the number of synapses itself, these are all things that affect how willing that neuron is to learn. And those are all things that can be targeted by plasticity. If you can make the synapse more sensitive, if you can add more synapses, if you can make it less sensitive, these will all change the propensity of these circuits to fire. And that is how we get working memory, short-term memory, and long-term memory. So long-term memory, that's where you actually got to grow new stuff, and that happens primarily during sleep. Short-term memory, you're changing the chemical organization within a neuron, and that can last for minutes or so, but then you can reinforce that. So you can say, oh, I needed to remember that I need to write something on a sticky note after class. So as long as every 10 minutes or so I keep reminding myself of that, that will stay in my memory. But I probably will forget that I had to write that sticky note tomorrow, because after I write something on that sticky note, I'll stop reinforcing that. So you've got all these different mechanisms for different timescales of plasticity that are bound up in this clever little device. So that is just a reminder of our basic neuron here. And that's all I'm saying here. Neuroplasticity, that's the change in shape, sensitivity, and number of synapses that can change over time and based on firing patterns. And so that's the elegance of this, is that although you can modulate this process, it's hyperlocal. There is not like a trainer that is sitting on top of your brain saying, this synapse here needs to be enhanced, this synapse here shouldn't be. These neurons feel the action potentials going through them. And through processes that we'll discuss today, based on how frequently they synapse, how frequently you get action potentials, firings, relative to how frequently you get firings in other neurons. That relative difference, how often am I firing and how often am I getting stimulus from an upstream neuron, a presynaptic neuron, that is going to affect how, if my synapse wants to beef up or wants to attenuate. And that local process of just, of action potentials happening, that is what underlies really all learning. We can then build systems on top of that that then use that to do more sophisticated types of learning. But when the rubber meets the road, that's actually what is strengthening these weights, is this very local process and a continuous process. We don't have a training phase and an inference phase, a training phase and an inference phase like we might do with some of our networks. But it's just kind of going on constantly. And that's what we're going to talk about today as well. So that's neuroplasticity, and those additional processes you can build on top of it are these neuromodulators. And so I mentioned in the honeybee brain, I showed that VUM neuron, which goes basically from the sensories, from the external system, the external world, let's say their antenna, up through, and it touches all sorts of parts of their brain. And when it gets a reward, then that VUM neuron releases a bunch of octopamine, which is like our dopamine, all throughout the brain. And it temporarily makes all of these synapses, it changes their sensitivity. So let's say it makes them more sensitive. So temporarily, things that wouldn't cause neurons to fire, now there's something more biased to fire. They have a little bit of an itchier trigger finger. They are more willing to fire. And as we'll see, if you can make these more willing to fire, you'll make the brain more willing to learn. So dousing the brain temporarily in these chemicals, which make these things temporarily more sensitive, allows you to build things like reinforcement learning out of a brain. Because at that point, you can say, well, normally, if you just happen to experience a pattern, maybe you'll learn it if that pattern is like really frequent. But we're saying that, oh, you just got a reward. If there's anything that's close to a pattern, I want you to learn that. And that's what happens. You get that reward and your body says, oh, you need to go into like pattern overdrive mode. Like your type 1 error rate has just been increased. We're going to allow you to make more associations than we normally would, because we know that you just got a reward and you need to figure out how you got that reward. That's how neuromodulation works. And this is largely something that, as we'll see today, has not yet really been tapped into when we talk about neuromorphic engineering. Largely, it's about the spiking. We haven't really got into this idea of like, can we broadcast a signal to suddenly make all neurons act differently for a short amount of time? But that is largely how your brain works, and how an insect brain works, and how all sorts of brains work. It's like that is one of the key things that makes learning happen. And as we'll see, it's gotten a little bit boring because people so like back propagation for those normal neural networks, then we're finding that in order to make progress with these neural networks, they've now introduced a way to do back propagation with these neural networks, again, just to sort of translate developments from traditional neural networks to these neural networks. And so that is very kind of not very biological, but it at least helps make progress in training these beasts, at least our versions of these beasts. All right, so that's our review. Any questions about the biological neuron before we now go into the neuromorphic versions? Okay. All right, so how do we get to neuromorphics? Well, if we look at the history of neural networks, which goes back very, very far, neural networks are very old. They got stale for a while because we just didn't have the computing power to scale them up to the numbers we have today. And I think largely they were kind of just less like weird, obscure little thing. And then suddenly we got a lot of computing power, and it became very easy to implement them and very easy to train them. And then they became sort of the workhorse of AI. when I was in grad school, they were not the workhorse of AI. There were all of this good old-fashioned AI stuff that were these other frameworks. They were much more cognitive. They were much more kind of mathy, but it just became so much easier to then use these kind of brute force neural network stuff that really didn't require a lot of theory, and it kind of took over. But they're very, very old. The first generation neural networks were these binary perceptrons. And so the activation functions were on or off. So you just viewed a neuron as being on or off, and you just had these binary neurons connected together. What we see today are what we refer to as second generation neural networks. And that's when you've taken the activation functions and you allow them to have continuous outputs. So that's our typical case there. Neuromorphics fall into what we're called third generation neural networks or spiking neural networks, SNNs. So these neural networks, their key adaptation, as I've hinted at already, is temporal coding. So they aren't going to, whereas second generation neural networks, the activation function level, whether it's high or low, that's what stores the information. But here, it's not the level of activation, it's how frequently it's being activated. If it's being activated very frequently, that's a high value. Not so frequently, that's a low value. This idea of that we should put this in our artificial neural networks is largely attributed to somebody named Carver Mead, who was an engineer, an analog VLSI, very large scale integration engineer at Caltech. So he's already was working on these very large integrated circuits, but he was an analog guy, not a digital guy. And so he was studying these specialized circuits that process analog signals at very high scale. And in thinking about that, said, you know what, that's kind of what's going on in the brain. And being an analog person, it was less about the structure. Like he said, we've borrowed a lot from the networks already. Like we kind of see how these networks are architecture. But if you think about how the neurons work, this isn't how our second generation neurons and first generation neurons don't really work the way neurons work in nature. And what if we made something that really acted like a natural neuron? So, and for him, the big thing that was being left out was spiking. So what if we built little analog devices that spiked and connected them together? Could we come up with ways to do computation with spiking neurons that looked like computation in nature? And if we could do that, maybe that would make them far more energy efficient for the reasons that I discussed, because the codes, the energy that you need, you only need to expend at these discrete time points. And in between them, you use very little energy. So if you could do spike-based computing, they could possibly be very energy efficient. And so it would be a little weird, though, because the analog, as we'll see in the simple models of the neuron that these are based off of, that each individual neuron is going to spike, it's going to leak, and it's going to have some recovery period, just like real neurons. And it doesn't feel very digital, so it's just kind of a weird perspective. But maybe it could save energy. And not only could it maybe save energy, but the kind of cool potential thing about it is that the biological plausibility might mean, and me personally, I don't necessarily buy this argument that if it's biomimetic, it's necessarily going to be better or whatever, but still there's kind of this idea that if it's biologically plausible, maybe that will end up leading us much closer to do the amazing things that real brains do. So maybe what we're missing isn't the network architecture. Maybe what we're missing are these physical characteristics. Maybe the spiking is that special sauce. And around this time, there were people like Rodney Brooks, who was a famous roboticist who he's the guy who came up with Roomba, and a bunch of other things. If you've seen like Kenny Benamor and some other faculty, have these robots, these giant robots that you can program by moving their arms around and showing them how to do things. That also came from his labs. So very famous roboticist, and in the 80s to 90s was trying to think about swarm robotics and was fantasizing about sending swarms of expendable robots to Mars, and wrote a bunch of, it actually wrote a documentary on this guy, and I can't imagine, like, that there being a documentary where combining him and a couple of other sort of people that were like, it was a popular documentary about this idea of this swarm intelligence and so on, and like in movie theaters and all that. I mean, it's just kind of crazy. And and he made all these promises about, like, by, I don't know, by 1990 we'll have, thousands of robots just running around on Mars. And then 1990 comes around and says, "Hey, Rodney, what the hell?" And Rodney, "Where's my jetpack?" And he said, "Well, it turns out that that you don't blame us. It turns out that the ants and bees and all these things are doing all these great stuff, but biologists haven't figured out." He actually used a term. It was like special substance. Like, he made it sound, it was a physical term that like people with a mass spec need to go out and find. They said biologists haven't found that special substance that explains this stuff, so you can't blame us because we can't put that into it. And so, so there was a need to look for what is that thing that's really differentiating between the cold hardware and the warm wetware. And spiking was Carver Mead's answer to that. It said, what we're missing is the spiking. If we just put the spiking in there, so many new things might be possible. And that's the kind of idea here. There are other interesting reasons why you might like temporal coding, and one of them, this asynchronicity, allows you to implement causal reasoning instead of correlational reasoning. Because right now, normal in networks, you take in all your inputs at a time. There's every neuron processes every input simultaneously and makes an output simultaneously. So there might be correlations in your data that, like a regression line, will be picked up by your artificial neural network. But your spiking neural network, because it's temporal, because it's asynchronous, theoretically could actually be trained so that only is trained on causal relationships, not just correlational. So if you happen to see an input just before another input, you might be able to learn that it's much more likely that the earlier input caused the later input than vice versa. But on an ANN, if those two inputs are relatively close together, you might just learn that they're correlated together. So that was another potential reason why maybe temporal coding would be better, is you could actually potentially tease out the difference between correlation and causation if you structured your training data correctly. That was kind of the motivation behind adding spiking. But what do I even mean by spiking? So let's look at that. So neuromorphics. And I'm going to keep using that term neuromorphics. I just want to highlight that here. Neuromorphic engineering. Generally neuromorphics are when we're using architectures that are meant to, with high temporal fidelity, mimic neurons. That's what we mean by neuromorphic. So they're not just the network, it's the devices themselves are trying to mimic the neurons themselves. And so in order to do that, those mimics need a model. And so we typically use spiking neuron models that were originally developed to describe the activity of neurons and then became models for developing devices that act like them. And so the simplest one that you see come up is this Leaky Integrate-and-Fire model that I'm going to talk about down here. So I'll just bring that up here. This can be implemented in hardware or software. You can download Python libraries. If you want to start building spiking neural networks tomorrow or today, you don't actually need to get access to hardware. You can implement these expressions, which I'll get rid of this tape here in a second, in Python or in software. And so a lot of spiking neural network development is actually done in simulation, in software. And that's totally fine. The idea is to eventually translate it into hardware devices that make those more energy efficient and so on, and actually realize all of these benefits. But you can do your development in software. You just basically simulate a bunch of ordinary differential equations. And the big target that most people start with is the so-called LIF model, the Leaky Integrate-and-Fire, or the Leaky Integrator model. And so this expression down here is a leaky integrator. So what do I mean by that? So, and this is another way to view it, is this is like an analog model of really a single layer perceptron. It's like an analog model of a single neuron. And so the idea here, and I guess I'll just get rid of some of this tape on the top here to make it a little easier to read, but is that we have a current coming into a total current coming into the synapses, the dendrites of a neuron. So you sum up all of that current, and so every synapse contributes a little bit of current, and those get summed up, and there might be some bias current, and you get a total amount of current coming into that. Just sort of at this point, it's anonymized. It's just a bulk amount of current coming into the neuron, and that shows up right here. And that current gets scaled. So this is, this membrane resistance basically is how much does every unit of current contribute to the neuron itself. And so you could imagine that synaptic weights could potentially change, this like parameters like this one here. And so that will cause current to either have a more of a hit to the neuron or less of a hit. And that current, so if we look at this, tau m dVdt, if you remember from a circuits class, you might remember that the current through a capacitor is C dVdt, where C is the capacitance and dVdt is the change in voltage. So if you are constantly, if you have a current source that has a constant current going into a capacitor, you're going to get a ramp of voltage. Because if C dVdt is constant, then if dVdt is constant, V must be a ramp. And that's where this comes from. So this is an idea that you have this membrane time constant is like a capacitance of the little capacitor that's built between the axon terminal and the synapse. That is like a little capacitor. It's like you got two plates and a gap. And so how close those are or other aspects of that gap can affect this so-called time constant, the capacitance, the sort of the capacity, like heat capacity, same idea. It affects how quickly you get changes in voltage for changes in current or for current. So as you're pumping current in, then what is the capaciousness of the neuron? What is the capacity of the capacitor? A big capacitor, if you put a lot of current in, hardly changes its voltage. And so the time constant would be very large. A small capacitor, as you put current in, the voltage changes a lot. And so it would have a small time constant. So that's where this time constant comes into play. And that's another thing that could be a learnable parameter. As you change the geometry or characteristics of the gap, then you change how quickly the neuron responds. So these are things that also could affect this. But the key point here is this minus V. So this V is the internal state of the neuron. So it is the voltage of the capacitor. So if I charge a capacitor up and now it's holding 6 volts, if I turn off the current, does it stay at 6 volts? Well, it's probably going to leak. And so that 6 volts is going to turn into 6.5, it's going to turn to 5.5 to 5, and eventually it's going to follow some decaying exponential back down to 0. So it's not going to hold on to that forever. And that's what this part is capturing right here. This is saying that if you accumulate information from the synapses, and that raises the internal voltage, I'll scale, that's fine. I'll call it internal voltage of the neuron. And then if you turn off the inputs, that internal voltage stays there for a little bit of time, but then it will eventually, due to this time constant, start to decay back down to its resting potential. And that's the leaky integrator. We haven't gotten to the firing yet. This is the leaky integrate part. So we've got accumulated information, which due to the derivative here gets integrated. So the relationship between this and this is an integral, if that makes sense. Because of, I is related to dVdt, then if you can get changes in I, you're going to get those will get integrated via dVdt into V. So the actual voltage on the neuron is an integration of the current going into the neuron, thus leaky integrator. So we have to get to the firing thresholds, but that's our leaky integrator part. Questions about that? It's basically just a capacitor model of a neuron. And I even could write that over here if it helps, like view it as a capacitor where you've got I equals C dV dt. That's our physics expression or our basic circuits expression. And then that ends up leading to something like that. Okay. So we've got those parameters. And the idea here, and this is just my explanation of this, this here is how much memory you've got. So how long does it take for accumulated memory to leak away? That's our time constant. That's our interpretation there. Over here, this is the influence of added current from this particular instant. So that current, remember, these are coming from other neurons. And as I've hinted at, those neurons are going to spike. So they're going to give you a burst of current at an instant. But that's it. They don't stay on. They just give you this burst of current, and that burst of current then gets accumulated inside the downstream neuron. So it remembers because the signal doesn't. The signal is fleeting, but the integrator remembers it because that's what happens with integrators. If you whack a bell, it rings because it accumulates information from that impulse. So you got a bunch of impulses here, and they get spread out over time due to the integrator. So then, and then this membrane potential, it is going to rise, but then if it doesn't leak enough away, eventually it will rise and cross a threshold, which I'll call VTH. Highlight that. And at that point, it releases a spike. And that spike becomes a pulse of current for the downstream post-synaptic neuron. And so that that brief increase, downstream synapse, that's also going to reset the capacitor to 0. So it's going to bring the neuron back down to 0. So it's like this, you've got this leaky capacitor that's got a circuit connected to it. And whenever the capacitor rises past a voltage, it shorts the capacitor out and sends a bunch of energy downstream to the next capacitor, which could then potentially rise and maybe fire itself. That's our leaky integrate-and-fire. So there's the leaky integrator and there's the fire. And so I'll show a diagram of this acting in time here on the next slide. But any questions about this? This little ODE model is what you can implement. You can implement a sim of this in Python, or you can build hardware. I can put capacitors on a breadboard that do exactly this. So I can build hardware that mimics this. And then I can wire up physical spiking neural networks, or I can simulate networks that behave this way with coupled systems of ODEs. And if you download a Python library for SNNs, it's basically just going to use an ODE solver and build systems of these things for you based on how you wire the networks up. Okay. So here's what one of those might look like in time. So let's say that I've got a neuron that has a constant input of current. Just pretend like, we can have constant input, it's not spiking, then what would the output look like here? Well, then, so this is the internal voltage of the neuron that is receiving that constant. And so because it's a constant input, then it rises to some point. It's sort of an exponential rise here. And then it hits the VTH threshold. And at that point, it spikes and it resets to 0. But because the input is still constant, it then rises again, spikes, rises again, spikes, rises again, spikes, and so on. So I here, so basically I'm saying this is like I of t is equal to c. I'll say is identically equal to c. That's what we mean by constant input. So I'm going to highlight that down here. And I'll just make these 3 lines look a little cleaner. K equals C constant. So what does that do? So then underneath that, these are the spikes. So this neuron is going to spike every time it hits threshold. So that's what its output is going to look like. So then if we think about if you get a stronger signal, then these are going to rise faster. And so instead of hitting. So if this rises faster because of stronger signal, it's going to hit here, spike here, hit here, spike here, hit here, spike here. And then now these spikes are going to be spaced closer together. If it's a weaker signal, then it's going to extend out as such. And so now we've got large gaps between the spikes. So stronger signals, faster rise, closer spikes, weaker signals, less likely to beat the leakage. And so you get fewer spikes, and you might get no spikes at all, because if the leakage is strong enough, then if you don't get enough current to overpower the leakage, then the leakage will dominate and you'll just never reach the threshold velocity or threshold, and this thing will just sit and acquiesce. So it's energetically costly to spike. It's not energetically costly to kind of rest. So if you're not spiking very often, you're not using up much energy. Okay, so that is our basic model, our LIF model. The strength of the signal is captured by the frequency between the spikes, or the frequency of the spikes, or you could say the distance between the spikes. All right, questions about that? That is our temporal coding of information. And what I hope we'll see is that, well, that's what I'll get to the next. Rather, I'll just go ahead and move forward. So this is, examples here of 3 different codes. So here are, for this period of time, the signal is very strong. It's intermediate here. It's very weak here. So over time this way, you get a pulse of strong signal, and then it's weak, and then strong, and then weak, and then strong, versus an intermediate, and then weak, and intermediate, weak, and intermediate, and then a barely noticeable in the weak, barely noticeable weak, and very noticeable weak. So if you imagine time going this way, this is how we're encoding that. Right now, we smell something exciting. That would be here. Right now, we have a hint that there might be something there, but we're not quite sure. It's sort of, may not even register. So that's kind of, how we're encoding things across time, is that density. If we were to plot the density here, then the density would go way up, would go down, would go way up, and go down. So really, the information is coded in the density itself here. And so that's kind of, that works well. It actually maps to other engineered systems that were not neurally inspired, like pulse width modulation and sigma delta modulation and sliding mode control of switching behavior and control systems. And so if you've ever had to control a motor with a digital output, then you find that you might have thought the first time you used a motor that you would just be able to set a voltage and say, I'm gonna give 2 volts to this motor, or 4 volts to this motor, or so on. And there are some applications where you have that, but they require expensive amplifiers. And in order for your little digital Raspberry Pi to say, I want 2 volts out, it can't provide enough current. And so you need to pass it to an amplifier that says, hey, amplifier, give me 2 volts of this amount of current. And that expensive amplifier can then modulate that output continuously. But more often than not, those cheap controllers are connected to cheap amplifiers that have 2 outputs, on or off, or maybe forward and reverse. And there's a so-called H bridge that allows you to sort of turn them off, turn them forward, or turn them in reverse, even if you only have 2 voltages to play with. So at that point, how do you change the speed of the motor, or how dim the light is? Well, you use pulse width modulation. So you say, I'm going to turn the motor on for 20% of the duty cycle and off for 80% of the duty cycle. So you say every 1/30th of a second is a duty cycle, and 20% of that I'm going to have it on and 80% off. And the motor's natural lagginess ends up averaging the signal out. So that a 20% duty cycle turns into something like 1 volt. A 40% duty cycle turns into something like 2 volts. A 50%, and so on and so forth. So you're now encoding things in space, or in time, not in space. And you're using the lagginess of the thing you're trying to talk to as an averaging filter to actually extract data from that. And that's really what's happening in this. This temporal averaging is really what's happening inside that integrator. That integrator is a low-pass filter. It's just filtering data out of this. And so the communication mechanism are these high-frequency spikes. But if you were to look at the field potentials, if you look at kind of what the voltages were inside these neurons or around these neurons, they might actually look a little bit more like smoother signals because they are filtering these things by the laggy action of an integrator. So that's part of what's going on here. So there is actually a translation from temporal coding to spatial coding and back, sort of in every neuron. Okay, questions about any of that, the temporal coding? Okay. All right, so how do we get these things to learn? So we're going to introduce here this type of plasticity that we've talked about before, but spike-timing-dependent plasticity, STDP, how spiky neural networks learn. So this is a causally reactive version of Hebbian learning, which we're going to remind ourselves what Hebbian learning is and define in that update rule a little bit later when we return back to artificial neural networks in a few slides here. But the basic idea is if I have two real neurons, so I've got this upstream presynaptic neuron A, synapse here, postsynaptic neuron B, and I'm saying, how does neuron B adjust its synaptic sensitivity? And it uses something called STDP. And what STDP does is it looks at the relative timing of firings presynaptic and postsynaptic. So if in B, in the cell body of B, where it's deciding how to set the sensitivity of each one of its synapses, it knows when it's received an action potential, when it's received a firing from A. It also knows when it fires. It uses the relative timing of those two events to decide whether to strengthen or weaken that synapse. So if upstream presynaptic neuron A fires slightly before B fires, then this AB synapse will be strengthened. So the sensitivity will increase. That will make it more likely for in the future an A firing to trigger a B firing. Now, I guess what I probably should have drawn in here is don't forget that B has got inputs from a bunch of other neurons. So what we're saying here is like A alone, initially A alone may not be enough to cause B to fire. But if B is also getting other inputs from other neurons and that the system of inputs that led to A firing also led these neurons to send signals, that will then, all of these together might cause B to fire. And then B will beef up its connection, its sensitivity to all of these neurons that all fired just before it fired. Then later, you'll need a subset of those to fire to be enough to trigger B. So this to me, and I don't know if this is actually what's going on, but a lot of times I have a hard time remembering one, and I know it's just there. And so what I'll do is I'll say something that is related and I'll listen to myself say it, and then suddenly that memory works. And I feel like to me, that's kind of similar to what's going on here. It's like I almost have enough evidence to trigger that memory, but but it's not quite there. And so I need to now bring more evidence in that tends to be associated with that memory as well. And the almost amount of evidence inside my head, plus the little bit of extra evidence, is enough to get my memory to activate. And then at that point, now that it's fired, then at least in short term, this synapse is increased a little bit. So that now, without me having to hear myself say, Washington, D.C., or whatever thing that I think is associated with that memory, now it's enough to sort of sustain itself alone. So that's kind of the idea here, is that like initially you need evidence, lots and lots of things to get a downstream neuron to fire. But as all of those things fire first, and then a little bit later, the downstream postsynaptic neuron fires, that postsynaptic neuron will be more likely to fire with less evidence in the future. And that will allow you to, and this is like, you could have a reward signal coming in here, and you might have evidence coming in here, or a stimulus. So you've got a reward here and a stimulus here. Well, if you get both of those happening at the same time, it might be enough to trigger B. And that will beef up the both of these connections here. But then in the future, you get rid of the reward, but now you have a really sensitive junction here, and that's enough that when the stimulus happens, you get the action even without the reward. That's kind of the idea here. That's the first half of STDP. If A fires first and then B fires soon after that, B then beefs up its connection to A. It also goes in reverse. So if the opposite thing happens, if B fires and then A fires, then B realizes that like, the input I got from A is correlational. It's not causal. For all I know, I'm listening to A responding to an action that I just caused. I don't want cycles of activity that aren't related to outside information. So I'm going to weaken that connection. So if A fires slightly after B, B reduces the sensitivity of the A-B connection. And that's it. That's spike-timing-dependent plasticity. That's what we think is going on, underlying pretty much all of learning. Again, this starts in, in short-term memory, gets consolidated into working memory, but that first short-term memory part of those fast time scale changes in sensitivity here, we think follow these rules. So questions about those rules. Does that make sense? The timing here. It's not simultaneity. It's the fact that A happens before B makes it stronger. A happens after B makes it weaker. Okay. And so we need to build devices that do this. That's what people have now done. So and then this is where the term comes. Spike timing dependent plasticity, STDP. And I'm just going to emphasize this is local, this is unsupervised, temporal, causally reactive learning. So there's no supervisor, there's no error signal. It's happening just right here. It's all implemented right here, totally distributed and decentralized. Okay. And that guy. Yes. And it's continuous, simultaneous training and inference. There's no training step separated from an inference step. You're doing it all constantly. You're constantly making inferences. And as you're making inferences, you're updating your training, happening simultaneously. Okay. So what are platforms that that are available historically and today to do spiking neural network work outside of just simulations on a computer? Well, one of the first ones, the first massive efforts of this was the SpiNNaker project. It's a massively parallel conventional computer cores, so basically a supercomputer that was all crafted specifically to simulate SNN behaviors like these in software. So the hardware was not spiking, but the hardware was specially designed, kind of like a GPU now is sort of now specially tailored for artificial neural networks. It was hardware that was specially designed to enable simulation. A little later then, IBM came out and they released their TrueNorth chip. This is a truly digital, event-driven chip that has a bunch of spiking neurons on board. It cannot learn through STDP though. This is made for highly efficient inference. So the idea here is you use a platform like SpiNNaker, for example, to come up with weights that are an optimal way to implement a spiking neural network for whatever task you want. Once you've figured out all of those synaptic weights, you then load them in just before runtime of TrueNorth. And then TrueNorth will give you an energy efficient way to implement that spiking neural network. But it's not going to do any learning online. It's just going to implement the weights that you picked some other way outside of TrueNorth. So then very efficient, doesn't use a lot of energy, but you can't do training online. More recently, Intel brought out Loihi. Loihi is like TrueNorth in that it is a hardware device that implements hardware spiking spiking neurons, but you can tune these neurons to do STDP. So Loihi can learn online. So you can actually have, and people do this, you can buy a Loihi chip, put it on a robot, like a flying drone or something like that, that's looking down at the ground, and then have it constantly do an unsupervised learning via STDP as it's looking down on the ground and finding patterns. And all of that is implemented in a very energy efficient way in this hardware platform, this continuous learning, doing exactly the process I talked about on the previous slide. And so this has been marketed for robotics and edge AI. So this is an older technology. This is back when we worried more about the batteries in our cell phones. And so the thought was, for one, we want to get the AI out of the cloud, so edge computing. So we're going to put all the inference out on the in the devices. So not only your phones, but other IoT devices. And these devices may not have access to a lot of energy. So how are you going to do this sophisticated AI? And so Intel said, well, you can buy our chip. And our chip not only allows you to implement energy efficient spiking neural networks, but it allows you to do the training in the edge and in a very energy efficient way. So that's how they kind of marketed these things. You don't see these chips everywhere now. I mean, so that's why a lot of it, if you talk to the Intels, the Amazons, the Googles of the world, I think you'll find a lot of these things are lost leaders. They build these things because they know the community's talking about them. Same thing with quantum right now. And then they get people in the door. And then when you're finally talking to the salespeople, they'll sell you this. But then they'll say, oh, by the way, what other enterprise AI problems do you have? Here's an existing portfolio of conventional tools that we also have available that we can bundle with this for you. And I think that is often what happens. So will you see a lot more Loihi in the future? Probably not. I mean, it's still there. I mean, Intel's got its own issues, but this is by now an old technology. But, I was on research projects, government-funded research projects 5 years ago where other performers were using Loihi off the shelf like a commodity element, similar to an NVIDIA GPU or something. So there are people using it, but it's just maybe not as widespread as, the futurists might have hoped for. So those are the kind of the big platforms that we talk about. They're all event-driven, low-power, parallel architectures. All right, questions about these three? The other there are more fancier, I guess, more state-of-the-art, novel, experimental ways of doing spiking neural networks. And one of these, which I like, is from, now it's getting a little old, but Boyn et al. 2017 in Nature Communications. They use memristors. And so memristors are like the fourth element. So, there's like capacitors, inductors, resistors, and so there's, if you go, there's sort of it was hypothesized that there should be sort of a fourth basic element, and it should have these features, this so-called memristor. And eventually people actually developed one and built one and showed you do have this fourth element. So what is a memristor? It's a memory resistor. Just like a transistor is a transconductance variable transistor, a memristor, memory resistor. And so it's this combination of things where I've got the current on the x-axis, the voltage on the y-axis, and there's this so-called hysteresis loop that evolves between current and voltage. And so if normally, like in a resistor, you would have a straight line here. So that's like, Ohm's law, right? So if you increase the current in a resistor, you increase the voltage across it. It's just, V equals IR. But because of this loop, which I'll explain here in a second, you get two resistances, and you get to choose which resistance you want. And it remembers the resistance you chose. That's where it comes from, memory resistor. So the idea here is that as you dump high current through this device, it eventually switches to a high conductance mode in that direction. So initially, if you're at this high resistance here, so you pump current in, you get massive increases in voltage. Once you get enough current in, though, it flips and suddenly the voltage drops. And then if you back out the current, you don't go out the way you came in. You come out this way. So that's what we call a hysteresis loop. So the history matters. So you start here, you increase voltage, and if you don't get over this hump, then if you just go back and forth in your current, your voltage will go up. It'll be in this range here. So for small current, you're this resistor. But when current is high enough, the device properties change. It reconfigures itself. So you dump enough energy in, you actually change the device. And at that point, it jumps to a different resistance. And so now, once it's this resistance, if you bring your current down, if you then bring the current back up, it will climb this resistance rail instead. So as long as you stay within this range, you'll be this resistor. So you're either this resistor or this resistor based on history. And if you reduce the current to go back the other way, so then eventually you can get switches back to the other resistance. So by modulating high current, you can switch resistances, which change and then use low current to probe those resistances. So you can set and read from these devices. And that's why they're called a memory resistor, memristor. So questions about that? Now, why am I bringing up the memristor? The memory is key. The element remembers it has its last resistance, so it's stateful. It stores one bit of state, and it does that in a persistent way. You can take power away from this thing, its resistance stays. It's non-volatile. So it's pretty cool. And this dynamic resistance can act like a dynamic weight. Because remember, the spiking neural networks, remember that it was like dv equals dvdt, tau dvdt equals minus v plus ir. R is a weight. This now gives me a way to make that weight change on its own. So I now can implement STDP if I build neurons where I use memristors at the synapses. Then that means that as you get a lot of current flowing through that synapse, then that synapse will switch to a lower resistance. And that will make it easier for current to flow through it in the future. So that's exactly what a memristor does. It does STDP. If you implement synapses with memristors, they'll do STDP. So that's what Boyn did. So they built this little experiment here where they implemented a so-called crossbar array. So if you're familiar with FPGAs, it's a similar idea. And with memristors at each junction. So it's just this array of wires. And so these wires form a grid, and then at the grid, you put a little memristor that connects the vertical wires and the horizontal wires. And then you just turn the thing on and give it, and then we're going to call this input and this output. What do we put on the input? So we're going to put MNIST on the input. So we've got a little MNIST code here. So we've got a little A, for example, and in little pixels. And then each one of those pixels, we're going to assign to an input row or an input column. So if a pixel's on here, a pixel is on here. Now, how do we assign it to that? We are going to use that Leaky Integrate-and-Fire. We're going to basically create a little pre-processing step, which turns ones and zeros via an LIF generator, a Leaky Integrate-and-Fire circuit, into spikes. So we are going to put current spikes down these vertical columns. And they're just going to go all the way down the column. Now, these memristors create pathways for that current to turn and also go down these pathways too. So if these pathways are grounded, that is another path for the current to go. So some of the currents is just going to keep going down, and and whenever they're going to also be turning and going down these ways. So you're going to get current all over this array. That is a key thing here. So you're going to have different current sources. So if this bit is on, this bit is on, this bit is on, if these 4 bits are on, you're going to have 4 current sources that are all going to come down through here. So theoretically, what can happen, and it turns out what does happen, is that if there are certain inputs that are frequently co-activated, then randomly speaking, there are going to be certain horizontal rails that are going to, just due to slight inconsistencies or a random initialization of the resistances, there are just going to be certain, I'll call them output pathways, that are going to accumulate a little bit more current than others for each given pattern. And if you have enough current, then these memristors are going to change their resistance, and they're going to make it even easier for current to flow, let's say, from this vertical to this horizontal. And if that happens with all of these, then you're going to get a lot of current flowing out here. And these memristors are going to hold a low resistance. And what Boyn et al. Did is they shined a bunch of MNIST, a bunch of handwritten A's. So there'd be slight variations on an A, slight variations on a B, slight variations on a 0, on a 1, a 2. So handwritten characters into that. And then they looked at what spiking outputs they got. And what they found is that they could, the spiking outputs were far lower dimensionality than the inputs. And each one of these codes that came out of here corresponded to a different letter group. So they were able to do unsupervised clustering with a bunch of wires and memristors. So that's an example where they could get this unsupervised learning or clustering just with STDP. So they didn't have training phases, there's no backpropagation or anything else. Just linking these things up together and showing them consistent patterns caused them to generate outputs that could predict which cluster, like not which letter type, not which image, which letter type. So all of the zeros got roughly the same code. All the ones got roughly the same code because all of the zeros had enough similarity that, like, my 0, the way I write a 0 might be this pixel, and this pixel. The way you write a 0 might be this pixel, and this pixel. But that's enough overlap for us both to generate a 0 code over here. And so the slight variations in the 0 aren't enough to not trigger this. And the large consistent in the zeros is enough to get this to eventually reinforce itself. That's an idea of how STDP can work in these arrays. So questions about that example? I just wired it up, showed it inputs, and watched its outputs change over time. Okay, so I think that's pretty cool. But what if we don't want to do that with spiking neural networks? Is there anything we can take back to artificial neural networks, second generation neural networks? And it turns out we actually can have a version, not of STDP, because we don't have that temporal nature, that temporal coding, but we do have Hebbian learning, those that fire together, wire together, which is really what STDP was sort of implementing in a neural substrate. So imagine we've got standard neurons, artificial neurons, standard A and N, like this one here, where we've got neuron A, so artificial neuron A, artificial neuron B. We've got the activation state, the output of the activation, I'll call XA, and the activation state of B, XB. And we've got a weight. So this is the weight that B has for the input from A, WAB. And I'm going to say that the activations, we're going to say, are continuous. They can take values from -1 to 1. This can also work from 0 to 1, but it just works even better with -1 to 1. So how do we update this weight locally without backpropagation, without some training step, just continuously update this weight in a way that's kind of like what we see in spiking neural networks? Well, we can use a relatively simple Hebbian update rule. So when you hear about people talking about Hebbian updating, this is what they're talking about. And so I say the weight, so this isn't a recurrent neural network. This is still a, we're just talking about a feed forward network, but the weights change over time. And that's why there's got this K+1. So the weight in my next time step is the weight in my previous time step. So really it's all about, this is the change in the weight over here, plus a change. And that change is going to be some learning rate, which is just a positive number, just like a learning rate in a gradient descent, times the activation state at A times the activation state at B. That's it, just a product of those two. And if you then think about it, if A and B agree, so let's say they're both ones, then that weight is going to increase. So, if they're both, we could say, what if XA equals XB is equal to 1? Then in that case, this is going to increase. If they disagree, then the weight will be weakened. And so in that case, if we have that A is equal to, let's say XA is equal to -XB, well, then the product of them is going to be negative and the weight is going to decrease. And that's basically it. And so with that, you can take that and do the Boyn et al. Experiment, but with an artificial neural network. And that's basically what I've drawn on the next slide here. So I've got that same update rule written up here. And I just set up a feed forward network with let's say an 8-unit output layer. I just 8 because 8 has sounded good. So I've got 2 possible output patterns that come here, and I'm going to feed it in a bunch of examples, let's say from MNIST, handwritten examples, little bitmaps of handwritten digits, and I'll here's a U, here's an A, and so it sees a bunch of these, and I don't tell it it's being trained. I'm just showing it inputs. And initially, the outputs are random. But if I show it enough U's at a time, then it starts tickling the same neurons or the same synapses for the U. If I show it a bunch of A's, it starts tickling the same synapses for the A's. And over time, you get a natural organization in the clusters. And you get this unsupervised clustering, just like we had in the STDP case. So unsupervised learning clustering going on with Hebbian updating. So inputs create correlations that get frozen in weights, making it more likely for a cluster ID to get triggered, even if the input pattern has a small variation. Same thing that was going on in the Boyn et al. Example, but implemented with more conventional ANNs. Questions about that? Okay, so rounding up here, looking forward, and then we got a wrap-up slide, and then we're done. Spiking neural networks, now they have recently, in the last, I don't know, 5, 7 years or so, developed back propagation. So there is a way to basically turn the spikes into a continuous approximation and then use that continuous approximation with something that looks a lot like back propagation to adjust the weights. And so it is a way to have an inference step be spiking and an error back propagation be continuous. And that has allowed people to start doing more supervised learning of these networks that it just opens them up to more applications. It's not very biologically plausible, but it at least makes them more practical to use. There's also crazy things that happen. Like, so I have a colleague, Maxime Bazanov at UCSD, and with the spiking nature of these things, you can feed noise into them. And this sort of unsupervised stuff that happens with the weights causes sometimes you to get, if you have noisy inputs to spiking neural networks, you can see replay of things they've learned earlier in the day. And so this looks a lot like dreaming. So you get reactivations of pathways that were originally strengthened during training. And what Maxime has shown is that if you train these neural networks on different tasks in sequence, so you train to see cats and dogs, train to see people and birds, and so on. Most neural networks, when you separate the training out that way, when you train them on task 2, they forget how to do task 1. But when you add this sleep phase in between trainings, you can actually recover the old task while learning the new task. So you do get some sort of consolidation that goes on in this artificial sleep, very similar to the consolidation that goes on in real sleep. So that's something that was enabled by using spiking neural networks. And now they're looking for ways to make that work, even in non-spiking networks, in ways that are inspired by the patterns they see in spiking. And then, as I mentioned at the top, neuromodulation, super important in real brains, really untapped in neuromorphics. We don't really have an analog for, suddenly wetting all of the neurons with dopamine and then draining all that dopamine off a few seconds later. That is just, we just don't have anything like that. But I think there's a lot of room for inspiration for that. All right, so that's all I got for you. So spike encoding, temporally rich, energy efficient, enables simultaneous learning and efficient learning in real time, learning and inference. Hebbian updating brings some of those aspects to good old-fashioned artificial neural networks, but there's hardware like Loihi and memristors that can implement STDP directly, so they can actually learn in hardware. They're not only efficient, but they may be the foundations of brain-like intelligence, whatever that means, and they better enable the quicker importing of other operational principles in real brains, like neuromodulation, sleep, and so on. So that's all we have to say in this class about neurons and neural learning. And so the one lecture that I have left for you is just a brief introduction to computational complex adaptive systems, things like the cellular automaton and things you can do when you combine evolution with CAs. So with that, I'll let you guys go. If you have any questions, feel free to come up. And otherwise, have a nice weekend.